Okay. Sorry for the delay, but I had some problem in broadcasting the video, so here we are now. So the last time we introduced the notion of functions and libraries, and we discussed about how to build a dynamic library, what is the difference between a dynamic library, a static library, and we saw also the preprocessor. We understood that the preprocessor itself can be used for doing some nice thing, like defining the minimum amount of values, and all the macros defined on the preprocessor would be evaluated at completion time, more or less. Now, going back to our slides, let's see, there we are. And how can, once we have understood what is the preprocessor, once we have understood how to compile a dynamic library, how can we use a dynamic library? Or better, how can we link the dynamic library we have just built to the executable we want to produce? I recall you the dynamic library is meant to store all the function we want to share with many different programs, and possibly one actually. And the idea is to have a kind of archive, a shared archive, which is loaded at the execution time by the executable, which needs any function inside the library itself. This is the idea behind the dynamic library. So to do it, again, we can use the GCC compiler and linker, actually, in this specific case. The full command we have to provide is the one you probably may see on the slides, but we will see later on a demo about it. So the idea is that behind the name of the source file, you have to provide three main things. The first one is the path of the current path of the library you want to link. Okay, and this is because I mean there is on POSIX systems there are some default, let's say, paths for the libraries, and so the linker first of all search on that. Well, first of all, exclusively search for on that path, unless you specify the path you want to search in. And so to do it, you have to provide minus capital L parameter, which is basically the current path of the library you want to link to your executable. Okay? Of course, you may provide many paths in which search, let's say, the library you want to deal with. However, in our simple example, we are only exclusively using one single non-standard path for the library, which is the current directory. And that's why on the command line we can see GCC minus capital L dot, meaning the library we want to build may be present in the current directory. This is just to let the linker where is the library we want to link to the current program, to the program we want to build. But of course, it might be the case that the library should be moved to a different location. Just imagine a situation in which your project not only contains an executable, but also contains a library. So before the installation, you need to compile both of them. So it could be the case that the executable you want to build should be linked to a library before the installation of the library itself. Okay? So it may be possible that the current location of the library is not its final location. And so we need a way to specify the final location of the library we want to link, which of course may be a non-standard library location, and to do it we have to use that weird parameter, let's say, minus capital W, L, comma, minus R path equal, and the final destination of the library, dynamic library we intend to link to our executable. Okay, so the difference between the first parameter and the second parameter is this one. The first parameter is simply meant to say to the linker, look, I'm just now, right now, I'm trying to link to a library which is in this location, and the second parameter is meant to tell the linker that the library which I'm linking my executable will end up in a different location. Okay. But we will see an example later on. So after we have provided these two parameters, we need a third parameter, which is a parameter with telling the compiler what's the name of the library we want to link to our executable. And the name is provided by the minus small l parameter, which has, let's say, a further parameter, as a sub-parameter, let's say, which is the name of the library we want to link. So if we want to link the library named libpeople.so, which is a dynamic library, we have to use the parameter minus L people. And automatically the linker pre-append, let's say, the prefix L, lib, sorry, and the suffix .so to our library name. Okay, and that's the way in which our program can be compiled and link at the same time to the library, in this specific case flib. Now this is the way in which we can link a dynamic library to our executable, but of course we may also be dealing with a static library, and things are almost the same, with the only exception of the middle parameter, which I recall you was meant to specify the final location of the dynamic library, so the location at the execution time of the dynamic library. Well, of course, since here we are dealing with a static library, which is, I recall you, meant to be totally included in the executable, we don't need to know the location of the static library at compilation at the execution time, because for sure all its content will be embedded inside the executable itself. So here we have to specify exclusively two parameters. The first one is the path of the library at the compilation time, and the second one is the name of the library we want to link to our program, and that's all. Okay. Now let's have a very simple example, and so let me see whether I can. Let's move to a terminal. Yeah, the terminal. Okay. Can you see it? Not really. So let me try to change. Okay, this is Oh, by the way, if you are connected on YouTube, please send me an acknowledgement. Just let me know whether everything is okay and is going as you may expect. Let me enlarge a little bit this stuff. Okay. Okay. So let's try to encode our first library, and let me use again gedit. As you may remember, the first library, well, the library itself must be split into two files. The first one should contain the definition of the function, and the second one is the header, and so should contain all the signature of the function we want to include into our library. So first of all, let me define all the library we want to deal with. Here I will first of all include this header, which again is meant to define the printf function. So if we want to use the printf function, we are required to include this header, otherwise it's not really useful. And here we may define something like the function fun, which takes no parameter and returns nothing. And this function will simply print in output, I don't know, have fun. This is it. Okay. And for instance, we may also provide a second function which can be unsigned int, I don't know, factorial. We talked about this function the last time, and actually we already saw the we already seen the code for it. So I assume you already understood what's going on with the code. Factorial n unsigned int press equal to 1 while for I going from 1 up to n I plus and press. Oh, yeah. Basically, I'm starting from assuming the factorial is to be at least 1, and actually this is the case because the factorial of 0 is 1, and then I keep multiplying my partial result by all the values going from 1 up to n, which is the formal parameter, and of course I end up with the factorial. This is our the source code of our library. Okay, quite clear. So here we have two functions. The first one simply printing the standard output message, nothing more, does not take parameter and does not return anything. The second one takes one parameter and returns an assigned integer and computes the factorial of a value. Okay, quite easy. Let me just check whether your colleague is still seems fine. Okay, great. Now let me save it. Okay, I just save it. Let me quit from it. Now, once I've written the the source code of my library, of course, I need also to define my header file. So let me do it in this way. I mean, I'm giving the same name, but let me change a little bit. I'm changing the name of the header file just to mess up the things and show you it's not necessary to provide the exact name for the header and the source. So the header will be first lib without this symbol. Okay, and so here we are. And so here I must provide the signature of the function I want to provide with my library. In this case, I have a library named fun and a library unsigned int factorial unsigned. These are the two signature of the function I want to provide with my library. Well, here there is small pieces of information I'm going to provide you, which is quite important from my point of view. Despite the fact this is a complete header, it may be the case that for some reason you try to include twice the same header. And if you left the header in this way, you may end up in a mess. The point is that whenever you define a new data structure, so the C programming language allows you to define new data structure, we will see by the end of this course. But unfortunately, it's not possible to define twice the same data structure, while it is possible to specify twice the same signature for a function. So we need to provide a way to avoid to include twice the same header in some sense. And how can we do it? Well, this is not really possible. So it's not possible to avoid to include twice the same header, but we can, by using the preprocessor, avoid to read, in some sense, the content of the same header twice. And how can we do it? Well, we can do it by using what we saw during the last lesson. So, for instance, by saying if it is not defined the macro, let me call it first lib. Okay. Well, in that case, define the macro. And read everything until we end up with what's going on with the and if. And okay. So by using this, that three lines, I'm basically saying if the macro first lib is not defined, define it. So once I define it once, I end up in avoiding all the code until avoiding to read all the code until the end if, basically. So the preprocessor discharges everything from the first line until the last line in my header. Okay, and so it's not possible to for the compiler to include twice the signature of the two functions we are defining here. Is it clear, this point? So even if I try to include twice this header, I end up including only exclusively one. But the header is included twice, but the definition of the function fun, for instance, the signature of the function fun is included exclusively once. Okay? And this is because if this macro is not defined, it's defined just after the if. Okay? So this is like a placeholder to say, look, this header has already been included into the code, so we don't need to include this stuff again. And this is it. So let me save it, let me close it, let me cut the two files. This is the first files with all the definitions, but I'm still here. Not yet. Yet. So, okay. So, this is the first file, as I was saying. So the one including all the definition of the function we want to be represented, be provided by our library, and this is the file. Instead, this is the file, the header file, which exclusively includes the signature of the function we want to provide. Okay. Now, how can we compile it right now? Well, first of all, let me compile the static version of the library. To compile the static version of the library, I need to compile all the source file in my. I want to include my library. In this case, we have exclusively one file. So again, I'm using GCC with the option -c. The option -c is meant to say, look, I just want to compile the source code. I don't want to link to any library for the moment. Okay. So if you remember, we had a schema in which we have the preprocessor processing the source code, then we have a compiler processing what the preprocessor has been already produced, and then we have the linker taking what has been produced by the compiler and producing the executable. Here, by using -c, we are simply saying we want to skip the last step. So we don't want to link our executable to anything. And here I need to provide the source file, and that's all. So by issuing this command, here we don't have any error because the source file hasn't any syntactic error, so no worry from the compiler. So by issuing this command, we end up with a file named firstlib.o. Okay, why firstlib? Well, because the source file has been named firstlib.c. So firstlib.o means, look, this source file has been compiled into this file. Okay. Now, of course, we may have many source files into our library. So we may provide, for instance, one single function per file, or many functions per file, but we may build up a static library by using many files, so many source files. So we need, in some sense, we need to collect all of them in a single library file, and this can be done by using the tool R, the command line R, which is meant to build up an archive. Okay, so to build up the archive, we also need to provide 3 parameters. In this case, we don't need to provide a minus b in front of the parameter. In front of the parameters, they are R,
to say that we want to place. Well, let me write the first of all. Let me write the full command, which will be, for instance, this one. Okay. So here we are building an archive whose name is flib_static.a by using the single file first_lib.o. So the binary content, the content of this file will be placed inside this file. So the -r means replace everything inside this file by using this file. The s parameter means you have to build up an index, so that when we are trying to use this library, the linker know everything about this file. Okay, and finally the c parameter is meant to say, look, I'm creating a new file. So by issuing this command, again, no errors, and we end up with a file named flib_static.a. Okay? So very simple. This is our static library, and we will see how to use it in a while. Now let's try to compile our library dynamically. So we want to build a dynamic library by using the source code we have just seen, and which has been used to build up a static library. So how can we do it? Well, in this case, it's much easier, even though you need to remember some more parameters. The first parameter you have to remember is fpitch, the fpitch parameter, which is meant to say we don't care about the position of our code. And the second parameter is the shared parameter, which is meant to say, look, we want to build up a shared library, so a dynamic library. And again, here we may write the lib, so the source code, and as output we may write flib, I don't know, let me call it, well, flib would be fine. Okay, let's try to compile it. Again, we end up with a file whose name is flib, whose name is the one we specified above. And this is a complete dynamic library. Okay, so these two libraries contain exactly the same code, but the first one is dynamic and the second one is a static library. Now let's try to use them. So let me write a piece of code which use, for instance, the function. So I don't know how to call it, main.c, for instance, and yeah, include, and well, okay, let me include the standard input-output header, despite the fact probably we don't need it. So we need to, well, let's try to use the library without providing any signature for the function we have just implemented. C char v and return 0. This is our template, and now let's try to find, well, first of all, print. I'm sorry for the indentation, but Unfortunately, I'm not able to see. Okay, this is a much finer indentation. Print the factorial. Something easier. And of course, okay, so here I'm basically calling the factorial function here and printing the output as a part of a string, and here I'm calling the function. Now let's try to save it and compile it as it is, so without providing any reference to the library, nothing basically. Well, let me erase that so here in class you can see much better. So I'm trying to do this stuff, and here I'm getting two errors. Well, more than two errors. The first two errors are error provided by the compiler. So the compiler is complaining because it's saying, look, you are using two functions which were not declared in some sense, so the signature were not available before the compilation. I can guess more or less what you mean, but I'm not sure that this is exactly what you want to do. Okay, so we are getting two warnings basically, because the compiler itself is guessing the type involved, the type of the number of parameter, type of parameter, and in the case of factorial, the type of the output, by looking at the code in our main file. But of course it is not sure that this is the correct way to do it. So we are getting two warnings saying, look, probably you have to declare this function, meaning you have to provide a signature for that. And the remaining two errors are linker errors. As you can see here, this is the linker, and it's telling us, look, there is an undefined reference to the factorial, to the function fact, which I don't know, and to the function fun, which I don't know either. Too. So first of all, let's try to fix this the first two errors, and to fix the first two, well, not errors but warning. To fix the first two warnings, let me go back to the main source file. Here we are, and we may say, look, include first lib.h. Please notice the difference between the first include and the second one. In the first include, we are using, let's say, this kind of parentheses, which are smaller than and greater than, to say that this header should be found in the, let's say, standard path for the header. So the system has a standard path for the header, which usually is in project system is usually /usr/include. Okay, and that's the standard path, let's say. Well, actually there are many paths, standard paths, but this is the main one. While in the second include, we are saying this header is not in the standard path, and since we are not providing any any path before, just before the file we want to include. This is in the current directory. Okay. So yeah, we are trying to compile this file, and to compile this file, we have to include this header, which should be present in the current directory. Now save it, close this stuff, and let me reset the terminal, and let me try to compile it again. Oh, sorry. This is not what I want to do. This is what I want to do. Now the first two warnings are gone, because we have included the header. So now the compiler knows the output type and the parameter type and the number of types of parameters for both of the fact and fun functions. But of course we are not still providing to the linker any library. So we are not saying, look, these functions are provided by these libraries. Okay, so there's no way for the linker to know where to get the two functions. You need to conclude the compilation of the main executable. So to do it, let me first try to compile in a static way our executable. As I said, we have first of all to provide the location of our library, so the current location of our static library, and to do it we have to use minus capital L. And then we need to, well, of course I need to provide the main, the source file of our executable, and then we need to say, look, we want to link flib static. Okay, so these two parameters basically say, look, the flib static is present in the current directory. Well, some of the library I want to link may be present in the current directory. Let's say much better statement. Let's say, and the binary code of the main.c file should be linked to that library. Now the linker understands that is a standard static library, and so is trying to build up the executable in a static way. This is it. Oh, okay. So if I have a look at the current directory, I end up seeing a.out file. If I try to execute it, I end up with the expected result. Okay, so let me rename it. So rename that file. Again, to rename a file, you simply have to use the command move, and let me call it static exec. Meaning that is a static executable. Now, what if? Well, we will see later on. So right now we are able to execute our code. We understood how to compile statically our code. And this is a nice thing to do, because we may have a library containing all the functions we need for many projects. We compile it once, and for all the project we don't need to record all the functions we intend to use, because we have the library. Okay, so our main project, let's say, would be the main file, and as you can see here, oh, the indentation is awful. I'll fix it later on. As you see, in the main file, which is probably one of the projects we are trying to build up, does not contain the code for fact and fun. Okay? So if we have many files and many projects involved the factorial function, for instance, we don't need to rewrite it many times. We can simply use the library we already built. And this is it. So let's try now to compile the very same project in a dynamic way. So how can we do it? Again, by using GCC. We have again to tell the compiler, look, some of the library I'm going to use may be present in the current directory. And this is done by minus capital L dot. And then there is a weird, let's say, parameter, which is this one, minus L minus R path, which, as I told you, is a way to say, look, my the final destination of my library, so my library at the execution time will be present in that directory. So if during the computation, you find a library which is required by my executable, one of the paths in which you need to search for it is the current one. And this is the case. So again, main.c minus L, and this is first flib probably. Let me try to compile it in this way. Okay, no complaint from the linker and the compiler. And if I have a look at the directory, let me redo it in a proper way, because I just created an nat.au file, but I want to provide a more intuitive name for it to distinguish from the static version of the file. So now if I try to see which file is present in the current directory and at the same time end with the exec suffix, we have two of them. The first one is the static executable, and the second one is the dynamic executable. Now, the static executable, we already seen it produce this output. Is if I have a look at the output produced by the dynamic executable, it's exactly the same. And this is expected because we have compiled the very same source code, but we have compiled it in two ways. The first way is by including the full library, the full content of the library into the executable, and the second one is to instead allow the executable itself, in some sense, load the needed library at the execution time. So if we have a look at these two files, we may see that there is a difference in the size of the two files. This is the size in bytes. Okay, so the dynamic executable is smaller than the static executable. And this is expected because the static executable includes into the executable all the code required to execute the file itself, while the dynamic executable load the code from the library. Okay, so this is it. Now let's try to do something nasty, for instance, and we may try to move the libraries into the directory libs, which I just created. So let's move lib, okay, into libs. So now in the current directory we don't have any more the two libraries, but because they have been moved into the directory libs. So if I have a look at it, I end up in seeing both of them. Let me see. Here we are. So now let's try to execute the two executable as we did before. First of all, let's try to execute the static library, the static executable, and as you can see, the static executable works as before. And this in some sense is expected. Well, this is for sure expected because all the binary code required to execute the static executable is embedded in the executable itself. So despite the fact we move the library from one position to another position, the executable can be run without any problem. And what about the dynamic executable? And we are getting an error. And why are we getting an error? Well, because inside the dynamic executable, we wrote that the library required to execute it is present in the current directory. And since we moved the library to a different directory, the executable is no more able to load it. Okay? Have you understood? More or less. What about you at home? So the idea is that we are missing the dynamic library to execute the dynamic executable. Well, of course, we may, since we move the dynamic library from the original position into the directory libs, we may try to recompile the source code. So again, how can we compile a source code and link it at the same time to a dynamic library? As we did before, by capital L, we are saying that we are saying where to find the library we are searching for, which is lib. Okay, then we have to say, look, the final destination of the library will be the same one. Okay, then we have to provide the source code of our project, and finally we have to say, look, we want to compile it. We want to link the source code to the library lib flib so. Now if I try to execute the dynamic library, oh, not fun. Oh yes, of course, because yes. Let's try to do it this way. No. What's going on here? Let me see. Oops, that's correct. So what's going on here? What? Equal mean. Oops. Why can probably this is correct. So what's going on here? Oh, that's the problem. The problem is that by issuing this command, I'm building up an executable whose name is a.out. So I'm not overwriting the previous executable. So if I try to run to execute the executable a.out, I'm basically obtaining the correct result. So that's what was the problem. So let me delete it and override the previous executable. In this way, now if I'm writing the running the executable dynamics executable, I end up with the correct result. Okay. And let me show one small thing. So, okay, let's assume that as I told you before, I'm building up a project which includes both an executable and a library. So before the installation, of course, you have to build both of them. So it may be the case that the current location of the dynamic library you want to link the executable is not its final destination. Okay, so let's assume, for instance, that during the compilation you have your library into the directory libs, but eventually you want to move it in a different directory. So how can you do it? We have just seen that if you, after the compilation, you move the library, you end up in a mess. So how can we compile something? How can we link an executable to a library which is not already in the correct position? Well, this can be done by changing the rpath parameter. So in this way. So in this way, I'm saying, look, at the compilation time, the flib library is present. Well, may be present beside the standard path, may be present in the directory .libs, but eventually it could be included into the current path. So by compiling my main file in this way, I end up in an executable. So there was no complaint from the compiler and the linker. I produce an executable. So let me delete the executable and repeat all the operation just to show you that everything went as expected. Here we are. But if I try to execute it, I'm getting an error. So the compilation was correct. I haven't moved the library until this point, but I end up in an error. Why? Because with the rpath parameter, I was specifying that the library may be moved to the current directory. Okay? So if I move the library from libs to the dynamic library from libs to the current directory, and I try to execute again my dynamic executable, I end up in success. Okay, is it clear? More or less? Okay, so now, what if we try to remove all the libraries we already built up? So let's try to do it. Let's try to remove libflib, and let's try to remove the static library, which is included into the libs directory. Oh, this is a directory, so to remove it we have to provide the -r parameter. Now we don't have any more the two libraries. Okay. If I try to execute the dynamic executable, I end up in an error, as just before, because we don't have any more the library itself. If I try to execute the static executable, success. Now this static executable can be moved to any Linux systems having installed in a machine having the same architecture I have in my laptop. So to say, every Intel compatible system in which I've installed Linux can run this static executable. Okay, so there are no dependency on what is installed or what is not installed into the system. And that's it. Any question? Is it clear? No, you seem... Are you okay? What about you? Okay, what about you at home? Okay, we will see it. Let's go back to our slides. But okay, I mean the last slide of the unit concerning function and libraries would be about what's next. So I'm not going to show you because I mean it's totally useless. Let's move to a different topic instead, which is nice. Here we are. So the next topic will be about arrays, pointers, and strings. So you probably, since you are coming from different programming languages, probably you already know this stuff. But let me introduce from the scratch for who is not familiar with the notion. And to do it, let me first of all present an example, a problem which can be solved by using what we will see by the end of the lesson. So the Italian lottery, or Superenalotto, is a gamble game, and the idea is that you have to forecast, in some sense, 6 numbers which are randomly extracted from how can I say, a box, let's say, without repetition. And the box at the beginning contains all the natural number from 1 to 90. Okay, 90. So at first you extract a number, then you extract another number, and so on and so forth. Of course, this game occurs twice per week, I think. I'm not sure, twice or 3 times per week. And it has no memory. So at each extraction, you start from the very beginning. All the numbers are placed, all the numbers between 1 and 90 are placed inside the box. And they have exactly the same probability to be extracted at each extraction. Okay, so at each repetition you have exactly the same chance to get exactly the same sequence of number. So despite this, so even if this game has no memory, there is always someone trying to keep track of a late number to guess what will be extracted next, which is totally absurd from a probability point of view. And they try to forecast what's next simply by remembering the number of extraction in which the number are not extracted, basically. So we are requested to write a program to track the delay of each number. I mean, again, from a probability point of view, it's totally absurd, but we are requested to do it for some reason. So a possible solution to track the delay of each number from 1 up to 90 is to have one variable for each number, and each of these variables are meant to store the delay of the number related to that. So we will have an integer to represent the delay of number 1, an integer to represent the delay of number 2, an integer to represent the delay of number so on and so forward till 90. At the beginning, the delay will be, at the beginning of the instruction, let's say, the delay would be 0, and then at each instruction we will have a variable saying, look, the number 10 has been instructed, and so by repeating an if block we will be able to increase the delay of a specific number. And this of course should be done for all the numbers in the box. Now the previous code is not really flexible, meaning that of course if you want to change something because I don't know, some of the rules change, or you discover an error or whatever you want, you have to change all the code in your program, and of course is extremely redundant, which as we saw is not a good thing for programs. So in this specific case, functions of course do not help, because we want to update the data structure, so we want to update the content of the variable, and we don't want to evaluate the function actually. So if you go back to our awful code, you see that each if condition will correspond to an update in the content of the variable associated to the if condition. So by using function, I mean you are not able to, at least for the moment, we are not able to do it. So what we really want is something that allows us to abstract the notion of delay of. We will love to have something like delay of and the number as a parameter. So to say we want a more structured data structure, which allows us to, in some sense, have a parameter telling us we want the delay, but we want the delay of that number. Okay? And this is actually provided by what is known as arrays. So an array is an indexed data structure to store uniform time of values having all the same time. So for instance, in this case, you can see on the slides an array storing 5 integer numbers. The first integer number is stored at position 0, and it's 3. The second integer number is stored at position 1, and it is 1. The third is -1, and it's in position 2, and so on and so forth. Okay? So, if I want to access to the fourth number, I must write a square 3 close square. Not square, sorry. Square bracket. Okay, and this way I'm able to refer to this position, so to the fourth position of our array. Again, nothing new if you come from any imperative programming language, but if you start from the scratch, probably you haven't seen anything like this before. Well, depending on the programming language, you may start from the index may start from 1 or 0. For instance, I think in Pascal and Delphi, the index starts from 1 instead of 0. However, I mean, this is a minor issue. You may understand what's going on in any case. Okay. Now, how can we use it? Well, first of all, we have to declare an array, just like a variable. To declare an array, we have to use this syntax, which is quite similar to the declaration of a variable, with the exception of the last part, in which again we have a square bracket, and we need to provide the length of the array. So we will need to provide the number of value we want to store into the array. So let me show you an example. Going back to our initial problem, instead of having 90 different variables, we have one single array which is able to store 90 values. Okay, so the first position we will have the delay of value 1, of number 1. The second position we will have the delay of number 2, and so on and so forth. Now, remember, the index of the array starts from 0. So the last valid index for the array in this case will be 89. Okay, but I mean, it's just a sliding. It's not very relevant. So at the beginning of our computation, we set all the delays to 0. So let's assume we want to start from the very first extraction in the Super Enalotto gamble game, and to do it, the delay at the very beginning will be 0, of course. Then at each extraction we may execute something like this. So for all the numbers in the box, we will increase the delay at the beginning, okay? And then for all the numbers which have been selected, and they will be contained by the array selected, we decrease the delay to 0. And that's it. Okay? So we highly reduce the sorry. We highly reduce the complexity of the code, and at the same time we in some sense generalize it. So right now we are able to handle the Super Enalotto game even if we, for some reason, who is organizing the Super Enalotto game decided to extract, I don't know, 200 numbers instead of 90. We simply have to change this piece of code. So that 90 should be replaced by 200. And the same thing is also hold for the number of selected numbers. So if at some point in the Super Enalotto, instead of forecasting 6 numbers, you will be requested to forecast, I don't know, 10 numbers. You simply have to change the 6 into 10, and that's it. If you go back to our previous nasty code, let's say, awful code, you have to copy and paste many times the same piece of code, and for each copy you have to change the name of the variables, which is awful. So in some sense this code is quite more handleable. Okay, and you can maintain it in a really easy way. Now, it's important to remember that differently from many other programming languages, the C programming language does not initialize array elements. So when you declare an array, the content of the array is a random set of values, different from 0. And so if you require initialization, you have to take care of it. I mean, there are compilers which take care of the initialization, but this is not default by standard. So it could be the case if you change the compiler and end up in something different because of that. Okay. I think, but I'm not sure about it, that probably is also system dependent, not only dependent on the compiler, because I'm not sure about it, but I think that, for instance, Mac OS tend to initialize the memory before really giving the memory to a program. But I'm not sure about it. So it could be the case if you compile the very same program with the very same compiler in two different systems, you end up with different results. So the best practice is to always initialize by your own the memory to avoid any issue in changing compilers and so on. So we understood how to declare an array, but how to use it. Well, to use it again, you simply have to use that syntax. So the name of the array, square brackets, the position we want to delete, and so on and so forth. So if that let's say syntax allows you to read the element position I in the array, what the variable I store. So what's the meaning of the variable I? Okay. Well, the meaning of the variable I is the address of the array itself. So the position in the memory in which you can find that array. The initial position of the memory in which you can find that address. If you remember at the very beginning of our pre-course, we had a slide in which we are talking about parking stars. And there was a red car and a bus. And I told you, look, there are situations in which data structure cannot stay in a single star. You are required to use many stars to memorize, let's say, your data structure. And this is the case. Okay, so to store a full array, you need many memory position, and the array and the value, the variable a represent the position in the memory of the array itself. So if you try to print a, you don't get the array itself, but just an address, a value, which is the position in the memory of the array. So again, this is quite different from Python, for instance. If you come from Python, if you try to print an array, you end up with the array itself in the standard out. But this is not the case on C. Okay? So if you try to print the array, you end up with a number. So what's that number? The position of the array on the memory. That's it. What is nice about array is that you can also use them as a parameter for functions. For instance, let's have a look at the example on the slide. Here we have okay, the main function. The main function declare an array having 10 elements, an array of integer a having 10 elements. At the beginning of the computation, we are assigning 1 to the very first element in the array, to the first cell in the array, and then we are calling the function test. The function passing as a parameter the array a. Okay. Now the function test has been declared at the beginning of our code block, let's say, and as you can see, we can see a strange, let's say, formal parameter definition. Why? Because the formal parameter definition is int a open square bracket, close square bracket. And this is a way to tell the compiler that the parameter will be an array. Okay? Now, inside the function, we are basically assigning to the first cell of the array the value 0. Okay? So we are changing the array itself. Now, what would be the result of executing this code, since after the execution test we try to print the content of the variable a? Can you guess it? Any guess? So can you guess the result of executing this piece of code? Remember, at the beginning we initialize an array, we assign to the very first value of the array the value 1, then we call test, the function test reset to 0 the content of that cell, and then we try to print the content of that cell on the main file, on the main function. So any idea? Can you try to guess what's going on? No. So you cannot even try to guess? No. Okay. Well, can you tell me why you cannot even try to guess? Totally lost. Okay, why are you totally lost? Because of? Ah, so you were distracted. Okay. Okay, great. So, anyone at home try to guess what's going on here? It changes from 1 to 0. Okay, so the test function changes the content of the first cell in A from 1 to 0, right? But then on the standard output, what we are going to get? 1 or 0? Well, we are going to get 0. And the point is that here, by calling the test function, we are passing the array, well, the position of the array in the memory. So actually, this parameter, so the parameter in the test function, the formal parameter, is a reference to the array. So by changing the array in the function test, we are basically changing the original array. Okay? And so after executing the function test, after calling the function test, we end up in a situation in which the first cell of the array A is has been set to 0. Okay, more or less. Okay, let's have a break. Sì, in realtà questo si potrebbe intuire da quello che ho detto prima, nel senso che lei alla funzione passa a, siccome prima ho detto che A contiene un riferimento alla memoria, diciamo, allora sta passando un riferimento alla memoria. Però in effetti se uno si domanda sempre se fosse per valore per cosa. E in questo caso è per valore. Il valore era il valore contenuto là. Ok.
So going back to to our discussion. So I was saying that at the end of the execution of this piece of code, we end up with printing 0. And the point is that here we are passing basically the address of the array to the function test. And you can guess it also by looking at the function call. In the function call, we are passing as actual parameter the variable a, which was meant before to be the array, the address of the array in the memory. So by doing so, we are basically copying that address into the format parameter, and then all the changes to the array A in the function test correspond to a change in the original array. That's it. So now, there is a different, let's say, in some sense, way to talk about the address of a specific data structure. So, by using array, we saw that the variable associated to the name of the array itself is an address to the array. But actually, we can also talk about the array of any data structure in the memory. This can be done by pointers. So, what are pointers? Pointers are very specific objects in the C programming language and C++ programming language, and are meant to store pointers are meant to store the address of data structure in the memory. Okay. So if I want to store, for instance, the address of a variable, to do it I need a pointer of that variable. And pointer, just like any variable in C, are required to be declared, and to declare them, you have to use the syntax you can see on the slide. So we need the type we are pointing at, the type of the data structure we are pointing at, a star, which basically means, look, I'm not dealing with a variable of that type, but I'm dealing with the address of variable of that type, and the name of the variable related to that pointer. For instance, if we have a look at this piece of code in the slide, here we are declaring a variable v, a standard variable, integer variable v, and at the same time we are assigning value 0 to that variable. Then here we are declaring a variable p, which is a pointer to integer. Okay? And this is done by the syntax int star p. By using this syntax, I mean I'm going to use a variable p, whose name is p, whose type is pointer to integer. Okay? And at the same time, while we are declaring this variable p, we are assigning to this variable something. And this something is the address of the variable v. So how can we extract from a data structure its address? We can use the ampersand symbol. So the ampersand symbol is used not only to represent the logical conjunction between two Boolean values, sorry, but also to extract the array, the address of a variable or of a data structure in general. So in this case, for instance, since the variable is a location in memory, which aims to store an integer value, of course it has an address, just like a car in the pack install, and to extract this address we use the ampersand syntax. So by writing ampersand v, I mean the address in which the value of the variable v is stored. Okay. Just imagine a box. You have the name of the box, but you also have the location which the box is placed. Okay. So the pointer related to the box can be obtained by using the ampersand symbol. So once we got the address of the variable v, we can assign that address to the variable p. Why? The variable p is of type pointer to integer. So this is more or less what occurs in the first line of the code. So in the first line of the code we have declared two variables. The first one is a standard integer variable. The second one is a pointer variable, and we are assigning to the pointer variable the address of the first variable, b. Now, have a look at the second line. In the second line we are doing something really weird. We are basically taking the pointer variable and applying the star syntax. What I mean by doing this? I mean, I'm not interested in the address itself, I'm interested in the content of the cell pointed by the variable. So meaning, I don't want to deal with the value in p, but I want to deal with the value pointed by p. Okay? Or the variable pointed by b. So in this case, for instance, on the left side we have star, on the right side we have of the assignment we have star p, meaning get the value pointed by p. Since p is the address of the variable v, get the value in the variable v, and to that value add sum up 1. So I'm right side of the assignment is more or less like saying v plus 1. Okay. Now, once I got that value, so this is simply an evaluation, I can assign again the value to the variable pointed by p. And to do it, I need to use the star p notation again. So by star p, I mean I'm not interested in the variable itself, but I'm interested in the location pointed by p. So again, the full line is equivalent to write v equal v plus 1. Okay? Is it clear? I mean, this is quite different from what you may have seen in Python, for instance, because in Python you don't have explicit, let's say, representation of pointers. However, I mean, this mechanism is quite powerful because you can, of course, use pointers as parameters. And this allows you to change the content of the variable you want to deal with. For instance, let's have a look at this piece of code. We have a function called dValue, which takes a pointer to integer p, and basically what it does is it updates the content of the value pointed by v by multiplying by 2 it. So first of all, you read the content of what is pointed by v. once it reads it, he multiply it by 2 and then reassign that value to the memory location pointed by b. Okay. Now have a look at the main function right now. So we have here an integer variable a assigned to 1, and then we are trying to call the d value, but not on a itself, because of course the two types are different. So a is an integer value, while the formal parameter of d value should be a pointer to integer. But we are taking the pointer to the variable I, and this is done by the ampersand syntax. Okay? So in some sense we are asking to a its address, and we are passing that address to the d value function. So once I've evaluated that function, what's the result of printing a in standard output, the content of a in standard output? The result is 2. Okay, so this piece of code is quite similar to what we saw for the array. So right now we have a mechanism to change the content of actual parameter. Well, not an actual parameter, but of a parameter, let's say. At the beginning of this lesson, we don't know how to change the content of a parameter. We know that functions are meant to evaluate something and return something else. Okay? So we were not able to change the content of what we are passing as parameter to the function. But at this point, by using both arrays and pointers, we are able to do it. Because instead of passing the value of a specific data type, so for instance a variable, we may pass the pointer to that data type. And that way, we are not only able to read the content of the variable, but we are also able to change it. Is it clear? Great. Now, what is nice about pointers is that you can also, as I just said, you can also use pointer to change the content of parameters. So, for instance, we can not only print the content of a variable, but we can also fill the content of a variable by using a specific function. For instance, to read from the standard output a value, we can use the function scanf. The function scanf read a formatted, let's say, text from the standard input, so from the keyboard, and place what has been read inside the location, the memory location provided as parameter. So in this specific case, for instance, I have 3 variables: a, which is an integer variable, c, which is a char variable, and f, which is a float variable. And I can read from the standard input exactly as reported by the first parameter of scanf, 3 values, which according to the percentage, let's say, notation, will be, first of all, a decimal number, second of all, a chart, and third of all, a floating point number. And the content of these 3 these 3 values will be placed into the memory location pointed by the variable a, or better, the memory location associated to the variable a, in the memory location associated to the variable c, and the memory location associated to the variable f. Okay? So is it clear why we are here using ampersand? Any guess? What about you? Is it clear why we're using ampersand? Really? More or less. Should I repeat it? Okay, so let me repeat it once again. So let's start from this morning. up to this morning, we know that a function is an implementation of a mathematical function and is able to, a function was able to read some data, some values as parameters, okay, and return a value. But it wasn't able to change the content of a variable, which comes from the calling function, let's say. Okay, so all during the calling phase of a function, all the parameters were expression, numerical expression, or I don't know, letters or whatever you want, however expression. Okay, so by calling a function, we were not able to change the content of a variable declared outside the variable, outside the function itself. So, for instance, let's focus on the printf function. By calling the printf function, for sure, we were not able to change the content of A, C, and F. Because by calling a function, we were able to pass the content of the variable, but not changing the content of the variable from inside the function itself. Okay? Is it clear at this point? More or less. Can you see my point?
It doesn't need to continue.
Okay. So the point is, if you call a function and you are passing variables, you are passing the content of the variables, not the variables themselves. Okay? Now, by using pointers, we are able to pass to function the reference to that variables. So instead of passing the content of a variable, we are passing the address of the variable, so the location of that variable in the memory. And because of that, we are not only able to read the content of the variable, but we are also able to change the content of the variable. Okay? So in this sense, by using the ampersand notation, we need the ampersand notation because we want to fill A, C, and F by using the values reported in the standard input. And that's why there is this, apparently different usage of the variable from scanf and printf. Because scanf needs to update the content of A, C, and F. And so need the address of them. The addresses of them. So their addresses. While printf exclusively need the content of the variable. So by writing A, C, F, I'm saying, look, report to the function their value. And that's all. Okay? Great. Now, this is a really nasty thing you can do in C, which is extremely useful. So, you will see why in the C programming language you have also the chance to perform arithmetic operation on pointers. What do I mean by arithmetic operation? I mean the thing you can see on the slide. So once you have defined a pointer, so a memory, a variable which is able to store an address in memory, you can also sum up to, for instance, to that address. Okay? Now, let's see why you can do this kind of things. And why the result of performing this operation seems so strange. So let's assume the address at the beginning is 0. It could be the case. Can you guess the final content of A after this piece of code? Can you guess it? So let's assume at the beginning the variable A contains 0. Can you guess it?
So, I think
Okay. So your colleague is saying that if at the beginning of the computation the variable a is assigned to 0, after the line you can see there, so after assigning to a plus 2, you end up with 2. So a will be filled by 2. Do you agree? No? Do you agree? No? You don't know? More or less, yes. I don't know. You don't know. Okay. To be honest, at the when I was a student, I couldn't understand why, but the result is not 2. And the point is that if I try to perform this operation, I end up with weird results. So let's assume we have a pointer to integer a. And at the beginning, the pointer to integer is set to 0, as we already assumed before. And let's try to...
the asterisk, I don't understand, because the first time we defined pointers, it was put right after int.
I see. So you are saying...
I don't know.
What the syntax was int asterisk space name of the variable, and here is int space asterisk. You're right, but actually both of the two are equivalent. Okay.
Thank you.
You're welcome. Yeah, actually both of the two are equivalent. So I mean, it's not really relevant. However, so thank you for the question. I mean.
It's clear.
No. I mean, it's really important because otherwise you don't know what's going on here. I didn't notice it because they are equivalent, but of course, as you just introduced to this domain, for you it's much different thing. So, but they are equivalent. So here, what I'm doing here, I'm taking a pointer to integer a, and I'm typecasting it to a different type of pointer. I'm typecasting to, again, a pointer of integer. I'm typecasting it to a character. I'm typecasting it to a double. Well, a pointer to character, a pointer to double. So, in each of these 3 lines you can see here, after the typecast, a became a pointer to integer in the first line, a pointer to char in the second line, and a pointer to double in the third line. Okay, so I'm changing the meaning of the type in some sense, the meaning of the value stored in A. Is it clear? Yeah. So by typecasting A, I'm changing the type of A. Okay. So in the first line, well, of course, A is a pointer to integer. Okay. But here I'm taking A and I'm typecasting it to pointer to integer. So it's a kind of pleonastic syntax. It's just to show you that it is exactly the same for all the typecasts. So in the second line, I'm typecasting it to pointer to char. So at that point, A is no more so the value in A is no more a pointer to integer, became a pointer to char. Okay? So now it's pointing to a character instead of pointing to an integer value. And in the third line, by applying a typecast, I'm changing the meaning of the value stored in A. It's no more a pointer to integer, it's a pointer to double, which is another data type. Okay? Once this has been done, I increase by 1 the array, the pointer. So I'm increasing by 1 the pointer to integer, I'm increasing by 1 the pointer to character, and I'm increasing by 1 the pointer to double. Okay? And then I want all these three values be printed in the standard output just as they was numbers. Okay? So basically, I'm taking a pointer to integer, I'm interpreting it like a pointer to integer and increasing by 1. I'm taking the same pointer to integer, I'm interpreting it just like it was a pointer to char and I'm increasing by 1. I'm taking again the same pointer to integer, I'm interpreting it just like it was a pointer to double and increasing by 1. And I'm printing in the standard output all these values. Okay? This is quite weird, because I'm keep repeating always the same thing. And the result was surprising. Why? You cannot see it, probably, because it's behind the desk. However, I'm getting, as a standard output, 4, 1, and 8. Why?
Is it because to represent the same, let's say A was a number, to represent the different formats, you need a different amount of memory?
Exactly. So let me repeat it for the guys at home. This is because to represent an integer you need 4 bytes. To represent a char you need 1 byte. To represent a double you need 8 bytes, at least in my system. Okay? So because of that, by increasing by 1 the pointer, I end up in the next free position to represent that data type. So if I take a pointer to integer, and because of the fact that to represent a full integer I need 4 bytes, by increasing by 1 that pointer, I end up in 4 byte next with respect to the original position. Okay? And this holds for any data type. So by increasing by 1 a pointer, I don't get the next address, but I get the next free address to represent that data type. So the data type associated to the pointer. Okay? So the point is, so to summarize, by summing a value n to a pointer, we are increasing the pointer value by n multiplied to the size in byte of the pointer type, which is quite clear, isn't it? This is my face the first time I saw this kind of thing. Okay. I mean, if you are not confident, this kind of stuff is totally messy. From time to time, I already get lost. So let's try to see an example just to figure out what's going on. So if the int data type is represented by using 4 bytes and p is a pointer to integer, then by increasing by 1 the pointer, I end up in p plus 4. Okay? Why? Because the integer data type is represented by using 4 bytes. So even if I try to increase by 1 the pointer, I end up in the next free position to represent an integer data type. Okay? And this is the equation which basically represents what's happening. But of course, it's tough to understand what's going on here. Okay? You have to get used. Okay, because of this, we can use pointer in place of array. Why? Because we can use pointer arithmetics to simulate, in some sense, arrays. And you can see it from this slide. So let's assume I've declared and filled an array by 0, 1, and 2. So the array is the array A, and by using that syntax, I'm basically declaring the array, initializing it at the same time. So the first position we will have 0, the second position we will have 1, third position we will have 2. By using the second line, we are assigning the content of the variable A, which I recall you is the address of the array, to the pointer P. So P is a pointer to an array, sorry, P is a pointer to an integer value, and we are assigning this variable P with the content of A, which is the address of the array A. Okay? Now, if I want to know the content of the first cell of the array, I can use the array syntax, which is done in the following way. You take the name of the array, you use the square bracket, and you write as an index 0. This is the first cell of the array, okay? But in the very same way, you can take the pointer, after the second line, you can take the pointer P and use the array syntax. So taking P, using the square bracket syntax, and you land exactly in the same value. Okay, so you can use pointer just like arrays. But also the other ways around is true. So you can, for instance, take the address of the array, increase it by 2, saying I want to take not the first element, which is in position 0, not the second element, which is in position 1, but the third element, which is in position 2. So how can I get the address of the third element? I can take the address of A and increase it by 2. And this gives me the position of the third element in the array. And then I can use the star notation to get the content of that address. Okay? Is it clear? I repeat it. So let's use A just like a pointer. A is pointing to the first position of the array. So to get the third position, we have to increase the A by 2. First position, A. Second position, A plus 1. Third position, A plus 3. Plus 2, sorry. So by increasing by 2A, we are getting the address of the first cell of A itself. So to get the content of the array, we need to use the star notation. The star notation, I recall you, is telling the compiler that we don't want to deal with the content of the expression, but we want to deal with the content of the memory pointed by that expression. Okay? So in this way, we are saying, in the way represented in the last line, we are saying we want to know the content of the first cell of the array A. But the very same thing can be done also by using pointers. So if the pointer P is assigned with the first position of A, just we did in the second line, we can get the third element in the array by taking P, summing up 2, and taking the star notation. Okay? This is really weird, but I mean, it works and it could be quite useful from time to time. However, despite the fact we can use the syntax of the array, we can use the array syntax on pointers and the pointer syntax and pointer arithmetics on arrays. They are not equivalent at all. They are not equivalent because pointers can be reassigned, so I can change the value of pointer, but I cannot change the value of the variable representing the array. So I can change the content of the cell, but not assign a new value to the variable A, which is the variable used to represent the array. Okay? So if you have a look at this piece of code, for instance, in P I can assign A plus 2, just to give you an example, but I cannot write something like A equal to A, well, capital A equal to capital A plus 2. Okay, so I cannot use capital A, which is an array, which is the name of an array, as a left term in an assignment. Well, this can be done for a pointer. Is it clear?
Yeah, I don't understand why, but okay.
Okay, because in some sense, if you do it, so you are asking why is not possible to do it? Well, in some sense, if you do it, you are losing the reference to the memory. And since you have allocated the array, you are losing the possibility, the chance to access to that array, which is of course a bad thing. And technically, this thing is called memory leak. So a memory leak is when you have a memory, you have in some sense reserved a space in memory, but you have no more the chance to access to it. And well, it's quite common for pointer to point to some kind of data structure and then change the pointer to something else, but you still assume to have the just to reach that kind of location in memory. Okay. So now we have seen. I mean, I don't want to use the word we understood, but we have seen. I mean, I know this part is quite tough and requires some time to be digested, let's say. However, we have seen the syntax, and at least you now know what's a square parenthesis mean, why we are using star. Probably you have somehow understood the meaning of ampersand, but I can understand it's not really easy to take it into 3 hours. But at least we can understand the meaning of this kind of stuff. So what if we find a signature of function whose single parameter is a char star b open parenthesis close parenthesis? What's the meaning of this stuff? But here I'm saying that the parameter will be an array to pointers of chars. Okay? So I'm passing an array which instead of whose cell, instead of containing values, contains pointers to char. Reference in memory to characters. Okay? So, do you have ever do you have seen something similar before? In the main, right? Great. So in our main, the second parameter was char star b open and close square parentheses. So the meaning of the second parameter is array of chars, array to pointers of chars. Okay, and what are used for? Well, they are meant to store the argument of the command line. So if you remember, the first parameter is meant to represent the number of parameter plus 1. The second parameter in the main function is meant to store all the words in the command line, including the name of the executable. So the first element in the arg V will be a sequence of character, an array of character, which contain the first word in the command line, and so the name of the executable. Okay? So if you want to understand what's going on, let's try to compile this piece of code and try to execute the program by issuing this command, for instance. And you will end up with parameter 1 is test, parameter 2 is my3, parameter 4 is 5.4. Please notice that here inside my constant test, I have a percentage %s saying that I want to represent the standard output, the string which is contained inside this cell of the array. Okay? We haven't seen it yet, but actually strings in the C programming language are represented as sequence, or better, arrays of characters. So we will see it tomorrow. Yeah. I think that for today is everything I want to tell you, and I think you have many things to understand during the night, so I don't want to push you further. Any question about what we saw till now? Okay, so if you don't have any question, that's all for today. And please remember, on YouTube you will find the video of this lesson, but also you will find a reference to the slides, and you also find a reference to the slides on Moodle, probably also some material about the lesson. However, if you won't have a question, don't be shy. Even though tomorrow morning, well, tomorrow afternoon, I think so. Yeah, you may ask them tomorrow in the afternoon, and I will try to answer to all your questions if you have some. Yes.
Are there any exercises we can try to learn?
I think so, but I don't know if I already published them. However, yeah, you may try. I mean, let's have a look at the Moodle side. Okay. Yeah. Probably you will find the example on the slides and something more already coded. Okay. So you may try to change things and see what's going on without the need of thinking an example by your own. Okay, thank you for the attention and see you tomorrow then.